Yeah. Oh, no, 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 no. That is my bad, not yours. Don't feel dumb reading that. That is my mistake. Hold on a minute.
I last 4th of July I had a house fire from an electrical box.
You had a house fire from an electrical box?
Yeah,
That's not good. There, this is better. Thank you for noticing, Jaslyn.
Around 4th of July last year, and we were displaced from our house for a week and a half.
Hello, hello, hello. So, I can live in my house. I just have no water, no electricity, and no heat. Other than that, everything is great.
You got it lost from the storm yesterday?
What?
You got it lost from the storm yesterday?
We lost it at 3 in the morning, not yesterday, but the day before.
Wow, because of the storm.
Yep, yep, yep. So.
I still see Unit 6 quiz Thursday.
What?
Well, that's because I didn't do that.
Mr. Brown,
Yes.
did you throw out all your food?
No, not yet. Why?
Oh, my friend lost her power and she had to throw out all of it.
Probably a lot of the stuff in our fridge will throw out, but hopefully our freezers are staying cold enough that it'll still be good.
So you have a
We'll see.
generator to your fridge.
Do you have power back?
Not yet. Not as of this morning, so hopefully by the end of the day today. Hopefully by the end of the day. We'll see.
Who was I talking?
Still doesn't have
Yeah.
power.
One
So.
of my teachers had a generator that they were giving. Who was that?
I don't know.
Doing explosion. Doing explosion today.
No, where do you see that?
It says implosion lab.
That I put out there, but we're probably not doing that till tomorrow. But we may take a look at it today if we have a little
Because I
time.
thought we were exploding.
It doesn't say exploding. It says imploding.
That's what I thought exploding for.
Alexa, no, Lucy.
What's up, folks? Prepare that.
Oh yeah, for the Pear Deck, ladies and gentlemen, there's your code. So go ahead and log into the Pear Deck while I finish taking attendance. That would be wonderful.
Victoria Drum perfectly helped Mrs. Olives.
Yep.
That's a whole lot of
Victorious drums perfectly help victorious olives. I don't know how the drums and the olives can both be victorious at the same time.
Don't judge the olives.
I'm not. I'm judging the drums.
Don't judge the drums either.
That's a funny code.
Well, they do come up with some interesting things for the Pear Deck. That is for sure. All right. 10, 4.
Mr. Brown, I'm proud of myself.
For what?
I'm already in May's unit for math.
So you're working ahead for math? Okay. Good for you. Good for you. So, ladies and gentlemen, again, get logged in. Thank you for noticing that. But let's remind you, you do have a quiz tomorrow, ladies and gentlemen. Okay? Your quiz will cover the following things. It will cover variables, meaning what are the 4 variables that affect the gas? Pressure, temperature, amount of gas, and the volume.
Well, we need to know units.
Yes, you will need to know units. Yes, you will need to know a definition for each of those things. We'll also cover pressure relationships. If you increase the amount of area, what will happen to the amount of pressure? If you increase the amount of force, what will happen to the amount of pressure? It will have temperature conversions, ladies and gentlemen, meaning going from 25 degrees Celsius into Kelvin, going from 425 Kelvin into Celsius. We'll remind you of how to do that because we did that yesterday and some of you weren't here. And then it also has relationships, ladies and gentlemen. In other words, if you look at a graph and the line is straight, what does that mean? If you look at a graph and the line is curved, what does that mean? If you look at the graph and the line is going up, what does that mean? If you look at the graph and the line is going down. So all of those things that we have been talking about this week, ladies and gentlemen, those are the things that will be on your quiz tomorrow. So thank you very much. Any questions on that? All righty. Okay, so let's take a look at the pear deck here, ladies and gentlemen. And again, this date is wrong on this slide. Your quiz is tomorrow. Okay. Today we're going to understand how to convert temperature and pressure into other units. Okay. And there is a worksheet out there. It is not due on 12/21/22. Sorry. It is due tomorrow. Okay. That is up here on the board.
I was thinking, why do we...
The reason why is because that was the last time I taught this class with last unit or last trimester with the group that did it then. That was the date that it was due. So I didn't update that. That is my bad. Okay. By the way, the worksheet is in Google Classroom. The key for it is also in Google Classroom. So we'll talk about that. But let's go on to this. Our first question, ladies and gentlemen. If we increase the amount of force, what will happen to the pressure exerted on something? Now, to do this, we're assuming that the area is held constant. Because if we're increasing the amount of force and we change the amount of area, we would not be able to tell what would be happening. So, simply increasing the amount of force, what will happen to the pressure exerted on something? Will it increase? Will it decrease? You cannot tell or no change. Slide your circle onto the one that you think it is, ladies and gentlemen. Let's see if we can get them all lined up.
No guarantee.
Never is, never is, never is. Only thing that's guaranteed is death and taxes. And I don't think death is guaranteed. I plan on living forever. Okay. All right, here we go. Oh, we did pretty good except for the cannot tell. All right, so ladies and gentlemen, what happens if you increase the amount of force, you increase the amount of pressure? It goes up. What kind of relationship is this? This is a direct. This is a direct. In a direct relationship, whatever happens to force, pressure is going to go the same exact way. That is what a direct relationship is. Good. If we increase the area a force is applied to, what will happen to the pressure exerted on something? So now we increase the area, ladies and gentlemen, what's going to happen to the pressure? Again, increase, decrease, cannot tell, and no change. There you go. Sneak it over there. Good job. Good job. Good job. Yes, it will decrease. Okay? The reason why area and pressure are in what kind of relationship? Inverse. Whatever direction one is going, the other is going in the opposite, ladies and gentlemen. The other is going in the opposite. Very good. Very good. Very good. So which of these graphs represents a direct relationship? And it is possible that there could be more than one. So please put your cursor on one of them that represents a direct relationship. Okay. I missed one. Which one did I miss?
The one on the bottom right.
The one on the bottom right is not a direct relationship.
That good one.
It's
The one on the top right is still a direct relationship. Why?
Because it's going straight.
No, that's going straight.
It's going constant.
It's going up.
Okay, but it's not asking anything about constant here. And that's not constant. What does a direct relationship mean? No, because then this one wouldn't be direct. What do these two have in common?
They both go up.
What?
They both go up.
Yeah, so which one did I miss?
The middle one.
I missed this one. This one's still going up. It doesn't matter how the line is going. A direct relationship means that the line goes upward. The line goes upward, ladies and gentlemen. So here, here, and here are all direct relationships. Okay? Which of these graphs, again, the same four graphs, represent a non-constant relationship? And again, there is more than one answer here. Put your cursor on one because you can't put it on two. Okay, that is a little bit troubling, ladies and gentlemen. Here's why. What do these two graphs have in common? Nothing. Nothing. This graph is going how? Up. This one is going down. Shape of this line. Shape of this line. Okay? So again, maybe you're not sure what a non-constant relationship means. I understand that. Okay? So again, let's go through it. If you are non-constant, it means that you have a curved line. Any kind of curved line is a non-constant line. And again, I will not try to make a line so that you can't tell if it's straight or curved. Straight, curved, curved, straight. Okay? So let's go back to what Zoe said a minute ago when we were looking at the last one and she brought in the term constant. Constant and non-constant have nothing to do with direct and inverse. Direct and inverse are simply what direction the graph is going. Is it going up or is it going down? That's direct or inverse. Constant and non-constant is what is the shape of the line. Is the line straight or is the line curved? If the line is straight here and there, that is a constant relationship. If the line is curved here and here, that is a non-constant relationship. If the line is going upward, here, here, and here, that is a direct relationship. Doesn't matter what the shape of the line is. All that matters is it's going up. Here, this is an inverse relationship because the line is going down. Questions, ladies and gentlemen? Okay, good. Good. Now, real quick, ladies and gentlemen, I want to review a little bit of the stuff from yesterday. Then we're going to get you back at the tables, which is where we kind of left off yesterday. So, for that, ladies and gentlemen, yes, Kayana, what can I do you for? There's one at the door. Didn't even hear a person knock. Sorry. Come on in, Jennifer. All right. So, for those of you who were not here yesterday, this is one of the two things that we talked about yesterday. And this is temperature conversions. And even if you were here yesterday, I would take out my periodic table and I would write this on my periodic table because I am not going to give you this on your quiz tomorrow. Not going to give this to you. There are two formulas that we told you to write down yesterday. Okay? Two formulas that we asked you to write down. Here is what they were, ladies and gentlemen. The temperature in Kelvin is equal to the degrees Celsius temp plus 273. That is how we will find the temperature in Kelvin, and that is what we are doing here, here, and here. So maybe it would be better for me to write it down here. Kelvin equals degrees Celsius temp plus 273. So we take 50 degrees Celsius, we add 273 to it, we get the 323 Kelvin. We take 85 degrees Celsius, we add 273 to it, we get the 358 Kelvin. We take negative 50 degrees Celsius, which you can have, a negative temperature in Celsius. We add 273, we get 223. Now, you can never have a temperature in Celsius lower than negative 273 because that would be a temperature of 0 Kelvin and you cannot possibly get any colder than that. One of my students yesterday while we were in class talking about this looked up the temperature of a vacuum in space, outer space, 2.7 degrees 2.7 Kelvin, no degrees. So even in the coldest portions of outer space, it doesn't get down to absolute zero. There is still a positive temperature there. Okay?
Is it always plus 273?
Always, 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 always. Now again, calculators sitting there, ladies and gentlemen. I expect you to use them on your quiz. Okay? But again, I'm not going to give you this formula on the quiz. You have to write it down. You have to know it. That's why I'm asking you to put it on your periodic table that you're going to use on your quiz tomorrow. Okay? Questions?
So it's K equals temperatures for Celsius plus 200.
Yes. So the Kelvin temperature is equal to the Celsius temperature plus 273. So when they give you that temperature, you add 273 to it, that will get you your temperature in Kelvin. And again, it is possible to have a negative temperature in Celsius. Yesterday it was below freezing outside. It snowed. Okay, that means the temperature was below 0 Celsius. Okay? Questions? The second formula we asked you to write, ladies and gentlemen, was this one. Was the temperature in degrees Celsius is equal to the Kelvin temp minus 273. So if you want to go from Kelvin back to Celsius, we simply subtract 273 from our Kelvin temperature. Here's our Kelvin temperature. Minus 273 gives us our degrees Celsius temperature of 152. 185 Kelvin minus 273 gives us a negative Celsius temperature, which is okay, at minus 88 degrees Celsius. Even a very high temperature like 1245 Kelvin minus 273 gives us a temperature of almost 1,000 degrees Celsius. Now you may be sitting there going, where on earth would you get a temperature of 1,000 degrees Celsius? Lava out of a volcano is much hotter than that. If you are working in a steel factory, to melt steel, you have to get it up at a temperature much higher than that. I worked at a plastic factory, where in the plastic factory, we would heat plastic up to hundreds of degrees to get it to melt, to then make it take different shapes and forms. Again, not unusual to have a very high temperature in Celsius, okay? It's not something that we experience in our everyday lives because our temperature ranges on the planet don't go that high. Celsius, a high temperature for us would be like 25, 30 degrees. That would be a hot day. Cold day would be like 0, -5, -10, okay? Doesn't mean we can't get it much hotter than that. Doesn't mean we can't get it much colder than that. Questions? Okay.
What's the coldest that something goes to?
The coldest that something can go to is absolute 0 Kelvin. Now, we have never gotten anything that cold, but that is the coldest you can get something to. Because remember, temperature is actually the what of particles? Movement of particles. What is the least amount of movement you can have? None. And that is what is called absolute 0. That is the coldest temperature possible. If I could get the particles in this tabletop to stop moving, they would have no temperature. 0 Kelvin. 0 Kelvin. Okay? Extremely cold. Questions? Other questions?
What happens when you freeze dry something?
Yeah, I never understood that.
I don't know for sure, but I think what it basically means is that you are getting it cold to somehow get the water out of it. So the water would separate ice over here and the substance would be left over here. I think. And I think in terms of freeze-dried, they're talking about freezing the liquid inside something so that it doesn't have that liquid feel to it, like a tomato has the liquid in it. If you get it cold enough, you freeze that stuff inside. Now it's considered dried because the liquid is not running out. Okay? Good question. Good question. Never been asked that before. Anything else, ladies and gentlemen? All right. Oops. Back to this. All right. Then we got into these pressures. Now, we're going to go to this right here, ladies and gentlemen, because this is what you're going to go work on in just a second. This is where we left you yesterday. Now, you'll notice at the top, I have the 4 pressures up here. Okay? So, let's go to this. And here's what you're going to do, ladies and gentlemen. You're going to go back at the lab stations and use them as your desktop, as scratch paper to write on. If you don't want to do that, you can come up, you can grab a piece of paper here, you can work on it on your desk. Most people like writing all over the desks in the back. We are going to convert from millimeters of mercury into PSI. To do that, ladies and gentlemen, I need this fact here and I need this one here. So what we are going to do is we are going to set up what is called a conversion factor. The conversion factor says I'm going to use 2 things that are equal to each other to go from one unit to another. Okay? You can convert from inches to feet this way. You can convert from feet to yards. Any 2 things that are equal you could use in this. In this case, we're using 2 pressures that are equal. The 14.7 PSI and the 760 mmHg. On the bottom, ladies and gentlemen, has to go the number with the unit that we are in. We are in mmHg. So 760 has to go on the bottom here, ladies and gentlemen. On the top has to go the number and unit that we are trying to get into, PSI. So we put 14.7 PSI on the top. Now it's called unit cancellation because when we look at this unit here cancels with this unit here because they're on top and bottom. Cancel across. And we would be left right now in the unit of PSI. Now to do the math, you are going to, in your calculator, take 815 times the number that is on top of the fraction, 14.7, and then hit divided by the number that is on the bottom of the fraction. So when we do that, that will be your math to figure this out. Okay? To figure this out. Someone have a calculator handy? Could do this math real quick for me?
15.7.
15.7 would be your PSI. Now, what? 0.8 with rounding. So what was the number after the 7, Zoe?
A 6.
Okay, good. So 15.76. That's the number you get out of your calculator. Probably have even more digits than that, but that's the number you get. But again, remember, in science, sig figs are important. How many sig figs in 815? There are 3. So this answer needs to also have 3 sig figs. Okay? So this is 1, this is 2, this is your 3rd sig fig. Meaning I'm going to round it to the 10th place, but I look at the number after, which is a 6. What do I do to that 7? I turn it up to an 8.
What did you cross? Yeah.
Here and here, I crossed off the unit of millimeters of mercury.
Okay.
Because we want the units to cross off. If millimeters of mercury were accidentally put on the top here, it would not cross off and you would not be setting your problem up correctly. Okay? Questions? Okay? Now, in this slide in your notes, in that box, all you need to type is that number 15.8. So we just did that, so type in 15.8 there. Okay? You don't have to put a unit because I have the unit up at the top. Okay? Questions? I can.
Actually, yes, I do have a question.
So we're basically like carrying it over for each column.
I'm sorry, Zoe?
We're like kind of like putting each column in like it like goes between so like it goes over and down.
Well, we're going to work across right now. We're going to work across. So I'm going to take this 815 in just a second, and we're going to go to the next part of this table, which is to take that 815 and now convert it into ATMs. So we will show you how to do that in just a second. Victoria, are you good here?
Yeah.
Okay. So if we want to go from millimeters of mercury to ATM, again, I still need millimeters of mercury, but now I'm also going to use this ATM here. Okay? And I'm going to begin with 815 millimeters of mercury. And I'm going to multiply it by a conversion factor. Now, the key to the conversion factor, ladies and gentlemen, is whatever I put on top and bottom here need to be equal to each other. I can't just make up numbers here. This number and this number have to equal the same amount, which is what all four of these do. This is still in millimeters of mercury, so the only way I'm getting rid of that unit is if I have what on the bottom here?
Mercury.
Millimeters of mercury. So I'm going to put that 760 again on the bottom. Cancels out, cancels out. Now, though, I don't want to go to PSI, so I'm not putting PSI on the top. Now I want to go to ATM. So I'm going to take and put the number and the unit of ATM on the top. 1.00. ATM on the top. So this is now set up so that we can do the math to convert from millimeters of mercury into ATM. Now again, what you're doing with your calculator is this. 815 times 1.00 divided by 760. Whenever we multiply by a fraction, the easiest thing to do is multiply the number on the top and divide by the number on the bottom. What do you notice about this number? What does that mean? Okay, so literally if you wanted to do this without this part here, it wouldn't change your answer. You could just take 815 divided by 760. But the only reason we can do that is because this is a 1. The last problem, we couldn't do that. It was 14.7 on the top. But if there happens to be a 1 in your conversion, you could ignore it if you wanted to. Okay? It's not going to change your answer. If that bothers you, put it in there. It's not going to change your answer either way. Okay? It's not going to change your answer. So what do we get for this one, ladies and gentlemen, when we do that math?
1.1 because the 7 rounds the 0 to
Whoa, whoa,
1.
whoa, whoa, whoa. Read me the number out of your calculator.
107.
Is there a decimal in there?
1.07.
07 what?
2.
Okay.
Because I rounded the 7 because the 7.
Why are you... Okay, what'd you round the 7 to?
The 7, I round the 0.
Whoa, whoa,
to
whoa,
a
whoa,
1.
whoa, 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 whoa. Slow down. Which is, again, 3 sig figs, right?
Right.
Which is the third sig fig in this number?
Oh, the 2.
No.
The 7.
The 7, but I'm going to leave the 7 spot. The 2 after it tells me, do I leave that 7 or do I round it up to an 8? We leave it. So your answer ends up being 1.07. 1.07. Okay? 1.07 ATM. 1.07 ATM. Questions? All right. Now, one last one to do, ladies and gentlemen. And that is to go from 815 millimeters of mercury to kPa. So again, I'm using millimeters of mercury, and this time I'm using kPa. Times a fraction. What goes on the bottom? Why is 760 on the bottom every time? Because that's what unit we're in. What if this were PSI? Then you'd put the 14.7 PSI on the bottom. Whichever one is the same unit, that's the one that goes on the bottom. That way our units cancel out. But now this time on top, 101.3 kPa. Okay. Do some math here. Get me a number. Now here again, Alex, you cannot, and for the rest of you, we can't, there's no 1 here. So we got to multiply by the number on top and divide by the number on the bottom. Okay? That is the math you are doing. 815 times 101.3 divided by 760 in your calculator. And then hit equal. What do we get? 0.63?
That's what I got.
Okay. Where's the third sig fig? The 8. So therefore, 109 kPa. Very good, ladies and gentlemen. Questions? All right. So here's what I would like you to do, ladies and gentlemen. We have done this first one. The second one, you're starting with 6.35 psi, converted into the 3 other units, then do the 2.69 ATM. Now again, ladies and gentlemen, if you want to go in the back and you want to write all over my tables with my chalk markers and use the towels that I have there to erase things and put your answers in here, that is fine. There's scratch paper up here if you would rather stay at your desk. If you need calculators, they are up here. If you want to work with a partner, absolutely correct. Victoria.
Was it 109 or was it 108?
It was 108.7.
But we changed it.
We round that to 109 because the 7 was the third sig fig. The number after it was bigger than a 5. We rounded up to 108. Or 109. Sorry, it was 108.7. We rounded up to 109. Okay?
So how would we get to mercury?
Well, you would start out with this, right? PSI. What would be on the bottom of your fraction?
The PSI.
14.7 PSI. What would be on the top?
The mercury.
The 760. Now it's going to be on the top because we're trying to get into it. Good. All right, ladies and gentlemen, let's get some work done. Let's get some work done. I will give you the answers in a few minutes.
I have an example.
No.
He said your situation is disaster. Well, every time they went to try to fix it, there was like it was.
Well, it was about 8 o'clock last night. We went to dinner at 6. Got done at 7. They're like, all right, we're going to drive down the river. They were still out there. We still had no idea.
Well,
And it
every
wasn't
time they fixed it,
WPS either.
no, because they had
Mike was there.
they had came in and finally arrived at like but yeah, your situation was not pretty.
Yeah, I know. So
He's like,
hopefully by the end of the
I'm
day
really
today-
sorry, but his whole deal was not.
Well, we have not opened the freezer. We have not opened anything yet. So hopefully everything is still frozen. So
Come in early and shower here.
I did. I came early. I worked out. I showered. Just went and got breakfast at McDonald's on the way. So
Yeah, so Brian didn't get home till 9 last night. And then he back in it. But he did.
Well,
When he
what
got home,
scared,
he's like,
what
oh, Brian,
scared,
I'm really sorry.
what scared my wife was she went on this morning at WPS's site and said, no issue, all fixed.
Oh.
And then she's like, well, we still didn't have any power when I left home. So then it said 222 houses.
That doesn't seem
He
right.
said this morning, it was
I got
4
the
hours, but less.
same thing I studied.
Yeah.
The mercury I studied with, I got the same
Heidi
mercury.
lives in, hold on. Well, you're not getting mercury.
I know.
Go for the
You're
first.
trying to get the same
So it was a
situation.
romantic evening at my wife and I sitting by the fire, her sleeping on the couch, me sleeping in the chair with candles going.
Oh yeah, you should see my friend.
When I go from
She
PSI to
they live in
mercury.
Oak Ridge up by us, and they,
When I get home,
she has 6 kids. They all slept by the fire. It was bad.
when I get home, every light in my house is gonna be on. Every room I walk into, I flip the switch.
Just in
Next
case.
time I'm here,
You never know.
like the bottom one right there.
Yeah. With the 14.7 PSI. Oh, because that's what conversion is.
The number that you start with goes here. These are always one of those numbers on the top.
Ah,
Okay. Now the last time, the reason the 760 was on the bottom every time was because we started out with millimeters of mercury. Now you're in PSI. Now put the 14.7 down there.
So that's why you ended up with the same number.
Yep. Yep. Oh yeah.
Yes. By the way, if you finish up, there's a worksheet today. And it's practice. You can go right to it. You can start working on it. If you want to stay back here and do it, if you want to go to your desk and do it, that is fine. Okay? So what's going on?
I think you're gonna
Alright.
I know.
We're doing here.
One of my teachers that I
Ethan's
had.
sitting there thinking you don't like him.
I know one of the teachers I had is in first master of math.
Yeah.
One of the house open the door, you have to have a teacher open the door.
Okay.